thank you very, very much indeed. It's a great pleasure to return to the Bournemouth Natural Science Society because I think it's a wonderful place. It's in the traditions of the Victorian learned societies, and it's a form of institution which has fascinated me as lying at the heart of so much 19th century and 20th century science. But I'm going to talk to you today about the nature of the transits of Venus. We are, of course, for people who perhaps are not connected, as it were, into the astronomical world, we are going to have a transit of Venus across the disk of the Sun on the 8th of June this year. Part of that transit will be visible from anywhere in the British Isles, and of course, if it's clear, you should be able to see it in Bournemouth. Let me say, though, initially, and before getting on to the historical importance of these transits, what a transit of Venus actually is. Venus, of course, is the planet which rotates around the Sun in a smaller orbit than we do. So in other words, Venus is closer to the Sun than we are. And so if you start at the Sun and you come out in the solar system, you have the Sun, you have Mercury, which goes around the Sun in 88 days, Venus, which goes round in 224 days, and us, which of course goes round the Sun in 365 and a quarter. So Venus is moving quicker in an inner. Now, when Venus transits the Sun, it means that the planet passes directly across the disk of the Sun. So that if you're looking at the Sun, or let's say, for safety's sake, you're projecting it with a telescope onto a piece of white paper, and you will see a nice, bright, sharp image of the Sun, probably with a few spots and other details on it, then you will see an absolutely jet black ball, or as it appears to us, disk, moving onto the Sun. And over the course of about 5 hours, it will pass from one side of the Sun to the other, and then go off it, and that's the transit over. Now, you may say, if you have Venus closer to the Sun than we are, why don't you get a transit of Venus every 224 days? Because after all, if you imagine a line going from the Sun's centre to the centre of the Earth, Venus must cross that line once every 224 days. The reason why we don't get a transit effectively once every 8 months or so, is because the planes of the orbit of the Earth and Venus are askew with each other. So in other words, if you imagine the Earth's orbit around the Sun, if you think of the Earth as not just simply a single planet moving around, but moving across a flat disk in the sky, the Sun is at the middle of that disk, and we are moving around the edge of that disk. Then Venus's orbit is another disk inside the big disk, and it's tilted to our disk, skewed at several degrees. So in other words, you vastly reduce the probabilities of getting a transit, because you will only get a transit when Venus's inclination and our inclination hit dead on. And that happens very, very rarely indeed. There is not a living soul on the face of the Earth who has seen a transit of Venus. And you can all see one on the 8th of June. The reason why no one's ever seen a transit of Venus is that the last one took place in December 1882. The one took place before that in 1874. Then go back beyond that, 1769 and 1761. And beyond that, 1639. There have only been 5 that have been ever observed and seen. And let me explain again a little bit why. You not only have these two disks that are what you might call asymmetrical with each other, so only when the edges of the disks meet can you possibly get a transit. But the mechanism, what is called celestial mechanics, the planetary astronomy that controls these motions, is governed by a cycle of 243 years. And in that period, you are going to get 2 pairs of transits in 243 years. The irony is, transits always occur in pairs 8 years apart. 1761, 1769, 1874, 1882. 2004, 2012. And between these pairs are varying cycles. And so in other words, this sort of mixture of planes hitting each other is very, very rare. Now, this is why transits of Venus are so very, very uncommon, and why no one has ever seen one. Now, why do you need to observe it in the first place? And to say this, one has to go back to the first person who ever observed and predicted a transit of Venus. And this is Jeremiah Horrocks in 1639. But before saying about Jeremiah Horrocks, let me give you an idea of where he got the idea from. And this came from Johannes Kepler, the German mathematician who really, created Kepler's laws and whose basic researches laid the understanding of what Newton would develop into the theory of universal gravitation. Now, Kepler, towards the end of his life, and he died in 1631, he predicted that there would be a transit visible in 1631, when Venus crossed the disk of the Sun. Nobody saw it. It happened, yes, and we were able to calculate in advance mathematically why no one saw it. Because it was only visible at that time of the day when it was dark in Europe. It would have been visible in America and over parts of Polynesia, but in fact not visible in European latitudes. And Kepler made the mistake of assuming that there wouldn't be another until 1761, 130 years in the future. Horrocks, of course, realizes that that was wrong, but I'm going to come back to Horrocks. I want to now to say something about the other planet, which goes around the Sun even faster, the planet Mercury, which whizzes around the Sun in 88 days. Now, we don't see a transit of Mercury every 88 days because Mercury's plane is also tilted as well. So these two inner planets are all tilted against each other on their axial planes, and you have to wait for particular times for lineups. But Mercury transits are much more common, partly because Mercury has what you might call far more bites at the apple. Kepler calculated that in 1631 there would be two transits across the disk of the Sun. One would be Venus, which was not visible from European latitudes. The other one was Mercury. And he predicted accurately that in November 1631, Mercury would pass the disk of the Sun. Why does he want to see it in the first place? The astronomers of the 1620s knew the moon and the Sun's position in the sky better than those of any other astronomical bodies. Kepler realized from the known diameter of the Sun, about half a degree to an observer on Earth, if Mercury was going to pass across the disk of the Sun, bang, you could point Mercury exactly in relationship to the Sun's center. And as he said, correct its orbit. So you could use the known position of the Sun to fix the known position of Mercury. And from that you could use it, as he said, to get a much more accurate knowledge of Mercury's plane. Now, the man who observes it is not Kepler. It's a Frenchman. His name is Pierre Gassendi, and Gassendi observes it in Paris with an assistant. And it's a bit potluck because you weren't even sure what day it was going to happen. Because after all, exactly knowing the day when this particular object would pass across the Sun with the level of planetary theory in 1631 was a bit hit and miss. Now, Gassendi used a technique first perfected by Galileo to observe it, because contrary to popular theory, astronomers in those days didn't look at the Sun through telescopes. We have this popular mythology that astronomers went blind because they looked at the Sun. That's a load of nonsense. Even Galileo, back in 1612, describes using a telescope as a projector, where if you align a telescope onto the Sun, it will produce an image for you, and you can observe all the spots and details and the transits on there. So you don't need to look at the Sun direct. Gassendi uses that technique. The problem is he doesn't know when it's going to start, and it's November, and days are short. He had an assistant keeping the clock, as it was called, because crucial to this observation was knowing exactly when the Mercury transit started and finished. Then suddenly, he saw a tiny black disk on the surface of the sun, smaller than expected, but moving rapidly. Now, he'd had a code for his assistant with the clock. He would stamp on the floor when the transit began, and the man was now to note the exact time on the clock. The assistant, unfortunately, had fallen asleep, and he had to go and shake him and wake him up. Even so, Gassendi's publication of the Mercury transit sets a whole new ripple going through European astronomy. If we can observe little planets moving across the sun's surface, we can relate their orbital position to the sun and get an understanding of their motion vastly more accurate than we'd had before. So that is what starts the transits of Venus. But nobody realized Venus was going to transit the sun 8 years later. Everybody was following Kepler. We won't have another transit of England until to a small parish called Much Hoole. It's about 15 miles from Preston on the road to Liverpool. In those days, it was in the depths of the Lancashire marshes. And the parish church of St. Michael of Much Hoole was a fairly new foundation, only about 20 years old at the time of the transit of Venus. Now, we know that a man called Jeremiah Horrocks was living in that parish. We know he came from Liverpool, where he was born in either 1618 or 1619. We know that he'd been to Emmanuel College, Cambridge, and what he was doing in the parish of Much Hoole, we simply don't know. Certain popular histories say he was the curate of the parish. He couldn't have been. He wasn't old enough. He was only either 19 or 20, and the statutes for the ordination of deacons in the 17th century, just like today, required a man to be at least 23 years old to be ordained deacon, on 24 to be a priest. Simply, he wasn't old enough. Now, he was himself a mathematician of brilliance, one of the most original and one of the most outstanding scientists this country has ever produced. He left Cambridge at 17. He'd gone up at 13. Now, this doesn't mean precocity, and people sometimes assume this. In those days, one often went to the universities in the way that one would go to a grammar school today. And your BA degree was something a bit like a modern A-level. Horrocks at Cambridge had clearly come to be bitten by the bug of modern telescopic astronomy. We know that he acquired a telescope. He speaks of a common half-crown telescope, which I suppose in those days was the Jacobean equivalent of a £40 beginner's instrument from Dixon's in modern money. But nonetheless, it gave him the key things he wanted to see. He'd also struck up an astonishing friendship with a man called William Crabtree of Salford. Now, Salford doesn't rank high in the annals of theoretical science, at least not until the 20th century, till the founding of the University of Salford. But in those days, Salford was a small chartered borough, literally connected to Manchester. The two of them were separated by the River Irwell, although they were separate corporate bodies. William Crabtree was referred to as a clothier or cloth merchant of that place. Now, the crucial thing is, this would have given him good connections outside Salford. London was the main hub of the English cloth trade, and from London, Flanders, and from Flanders into Europe. Therefore, my suspicion is that Crabtree's working as an entrepreneur in the cloth trade gave him connections to the continent. We know that he owned books by Galileo, by Kepler, by Descartes. He read fluent Latin. He'd been to what was called the Manchester School, what would of course have been the Manchester Cathedral School, later what would have become the Manchester Grammar School. And although Crabtree had never been to university, he nonetheless was clearly literate in Latin, Greek, and probably French, which he would of course acquire in his native parish. Now, people, therefore, when they tell you that in the depths of the countryside in those days, people lived in primordial ignorance is not quite clear. Crabtree is about 10 years older than Horrocks. We think he was born in 1611. What we do know, though, is that Horrocks had a contemporary at Cambridge, a man called John Worthington, who was also a member of Emmanuel. Worthington was a Mancunian. In those days, of course, for every university vacation, you didn't go home. It was a long, long walk from Cambridge to Lancashire. You probably went for the long vacation. And I suspect that Worthington and Horrocks made their trek from Cambridge to the northwest. And at the time, of course, when Horrocks would have still been living with his family in Liverpool, probably Manchester was the last day's walk before Liverpool. And I suspect he stayed over with his friend in his family's house. Horrocks probably met William Crabtree in that connection, the famous local astronomer of the area. We don't therefore know beyond that how they met, but they struck up a friendship in 1635 which generated scores of surviving letters. They start to correspond between 1636 and 1641 on matters astronomical. Between them, they make these discoveries. They make the first clear proof that the moon's orbit around the Earth is an ellipse and not a circle. Not bad. That would get you a Nobel Prize today. Not bad for two chaps working in the country. Horrocks also concluded that the moon had no atmosphere, because he'd made an observation in 1637 where the moon, what was called occulted, or passed across the Pleiades cluster, bright cluster that you can see any clear night during the winter. And Horrocks had argued that as he saw the dark edge of the moon going across the cluster, each star was snuffed out instantly, like that, suggesting that had the moon had an atmosphere, there would have been flutter or flicker before the stars vanished. Ergo, the moon has no atmosphere. He also did important work. Now, at some stage in 1638, Horrocks takes up whatever job he had in the village of Much Hoole. And like I said, we can date this because suddenly he starts to put Much Hoole on his letters and not Toxteth, well, what was then, of course, the village just outside Liverpool where the Horrockses lived. Now, in October 1639, he writes a hurried letter to Crabtree. And he says, I believe that about the 24th of next month, 24th of November, Venus will pass across the disk of the sun. He said he had analysed several printed tables of the Venusian motion which he then had, compared them to his own observations, and came to the conclusion that Venus would not pass above or below the sun, as it usually did, but bang across it. He says, I believe Kepler was wrong. Kepler said we will not be getting another transit until 1761. I think we'll be getting one next month. Both men kept watch. Now, the 24th of November, 1639, was a Sunday. And it's this which gives some of the arguments and suggestions that indeed Horrocks was somehow working in the church. Because Horrocks makes several remarks about being called away at different stages in the day to callings of a higher kind, which could, of course, have been celebrating the liturgy or assisting with the celebration of the liturgy in church. Now, we know that towards the end of that day, he'd seen nothing. He says he'd set up his telescope, and he tells us in detail what he did. He had a pole. He had his telescope at one end of the pole, a little screen at the far end with a piece of paper on it divided into 360 degrees, very, very accurately drawn, so that the image of the sun completely filled that circle, so that no matter what point Venus entered the sun's disk, he could mark it to within a degree, and hopefully mark it to where it would leave. You'd had cloud all day. Nothing visible. He clearly kept popping out at every stage, and then at 3:15, the sun, of course, is only going to be up for another 40 minutes. There is a sudden break of the sky in the west, and a flood of sunlight goes across the country. He gets his instrument upon it, and what does he behold? Venus as a beautiful black disk. The transit's already started, because Venus is already a few minutes of arc into the sun. Over the course of the next half an hour, he recorded 3 further observations, and each of these showed that Venus was creeping slowly deeper into the sun. And then the sun went down. He, of course, writes to Crabtree to know if he's seen it, and Crabtree has seen exactly the same thing. Clouded out all day, And probably the same break in the clouds which he saw in Much Pool, Crabtree saw in Salford, 25 miles away. He saw it as well. Both men recorded exactly the same features on the surface of the sun. This was, frankly, a triumph, astronomically, of theory. Now you may say, what do they do about it? Well, Jeremiah Horrocks writes a treatise on the subject. It comes to be called in its ultimate Latin publication, Venus in Sole Visa, Venus seen on the face of the sun. And from it, Horrocks draws some very, very powerful conclusions. He says the first thing that staggered both him and Crabtree, because both men pool their results in this book, is that Venus was so unexpectedly tiny. Everyone believed that Venus was 3 arc minutes across, and it should have blotted out about, easily a quarter of the sun's disk. But it was a tiny little black ball. Why? Horrocks suggests, and this is an extraordinary suggestion, that Venus might actually be, yes, quite small, the ball of Venus, but there might be something very shiny around it. In other words, some kind of atmosphere that gives it the brilliant glow of Venus in the evening sky. Why, therefore, is that thing so incredibly bright in the sky, but such a pipsqueak little thing when seen on the sun's disk? Horrocks suggests it's because of some kind of reflectivity around it. And here you see from Horrocks what a dirty-minded teenager he was, because he makes this rather amusing remark. He speaks of Venus, who of course was both the Greek and the Roman goddess of love, and of course the epitome of beauty in classical art. Venus is modest, and Venus always drapes herself so you can't see her body. But in the same way that you can see somebody if they're standing against bright sunlight and the sun shines through their clothes, so when Venus is on the sun's disk, you can see Venus's naked body. In other words, stripped of what he calls her shining raiment. Now, it's a rather poetic, slightly risque analogy, but he uses it. It's perfectly correct. And this gives him this idea, therefore, that Venus is a small planet with some kind of shiny envelope around it. But also then he was able, from his 3 observations, to relate Venus's position to the center of the sun, and enable him to get a complete new correction or complete new position for Venus and Venus's plane in the sky. So he's recognized its tremendous powers of correcting orbital theory. He then continues to observe Venus for several months, because of course then Venus slides off the sun, then appears as a morning star for several months. And from observations of Venus as an evening star, observations of Venus on the sun, then observations as a morning star, he was able to draw the conclusion that Venus probably goes around the sun in an elliptical orbit. In other words, to extend Kepler's work to Venus. Now this is a pretty profound conclusion. Crabtree in Salford sees the same things and draws similar conclusions. But then the whole business ends in death. Horrocks dies suddenly and of what cause we don't know on the 4th of January 1641, 14 months after the observation. We don't know what killed him, he simply dies suddenly. And then in 1644, William Crabtree died at the age of 34, 35. We don't know what of again, probably of an infectious disease, the commonest causes of death in those days. All that we know is that he was buried on the 10th of August 1644 in the grounds of Manchester Collegiate Church, where he would have received his education, because we have a burial register for him. What he died of, we don't know. But then, Horrocks' Venus in Sole Visa is published in 1662 in Danzig in Poland. How it got there, I have no idea. But it was published by the great Polish astronomer Johannes Hewelke in the Polish, or Johannes Hevelius in the Latin version of his name that he published in his international publications. Now, Johannes Hevelius was another amateur astronomer, but he was a far, far, far from poor one. He owned the biggest brewery in Danzig. He supplied beer to the Swedish Navy on an industrial basis, and this allowed him to equip one of the most magnificent private observatories on the face of the earth. He even owned his own printing press where he published his own books. How he had come across Horrocks' manuscript, I have no idea. But he publishes it as a sort of a tribute, and his friend the dead become immensely famous posthumously. So this is the first transit of Venus, what in fact came to be recognized as the birth of modern research astronomy in Britain. And it's rather ironic that the birth of that astronomy was not in a royal court, or in Oxford or Cambridge, or any great learned society. It was in private houses in the northwest of England. Well, I put this photograph in from the 1874 transit because it actually shows you what you should see. Here's the sun's disk, that's Venus, and of course it gives you the perfect proportion of the relationship of Venus to the sun's disk. That's exactly what Horrocks and Crabtree would have seen in 1639, and of course over the course of about 5 hours, Venus would move from one side of the sun to the other and then exit. This is his friend William Crabtree, a portrait by Ford Madox Brown in Manchester Town Hall. This picture is about 1880, showing Crabtree also observing on the disk, and there of course you see Venus creeping onto the projected image of the disk. But following the well-known Victorian conventions that intellectual heroes all had to look worn, wan, consumptive, or demented, I should point out that Crabtree at the time was 29 years old. This is another 19th century portrait of Horrocks, allegedly observing the transit of Venus. He was an immense, the event of 1639 was an immense inspiration to so many Victorian artists. This is the window, a 19th century window, the Horrocks window in the Church of St. Michael, put in the 1860s, I think it was. And the inscription is, of course, the word of the Lord shall endure forever, religion and science in fellowship, 1874, 1639. And another part of the Horrocks window inside the church is this rather beautiful stained glass window showing the young Horrocks observing the projection of the sun and Venus on a sheet. This is Carr House, owned by the local Stones family, who were certainly the only family in the area likely to have engaged a tutor for their children. And another legend is Horrocks observed the transit from this house about half a mile away from the church. Now we go to Edmund Halley. Now, Edmund Halley knows he'll never see a transit of Venus. Halley was born in 1656. He was born, in other words, 2 decades after the Horrocks transit, and knew there wouldn't be another to 1761. Now, Edmund Halley never saw a transit of Venus, but he became fascinated by them. Now, in 1678-79, he spent 2 years on the island of St. Helena in the South Atlantic. Now, there he happened to see a transit of Mercury. Already, of course, several had been observed. Hevelius had observed one in 1661 and things of that sort, for instance. So transits of Mercury, much, much, much more common than the Venus transits, were observed. But the problem is you couldn't do much with a Mercury transit. The dot of Mercury is so tiny and its movement so quick, the instruments of the day couldn't really do a great deal with it. They recognized that Venus was much better for correcting solar coordinates. Now, I have observed this thing deep down in the southern hemisphere. Who might have observed it in Europe, in London or Paris or Bologna or somewhere like that? Because if you had, this occurs to Halley inspirationally, if you'd had a cluster of observers observing the Mercury transit of 1677, and when they all came together, they pooled their results, they would all have seen Mercury transiting the sun in slightly different positions. Because if you were in the southern hemisphere, Mercury would appear a bit slightly higher up on the sun. If you were, let's say, in St. Andrews, very high up, Mercury would be a bit lower. And by comparing this spread, and by knowing the exact relationships of these places to each other on the Earth's surface, you could calculate the distance of Mercury, using a sophisticated version of the kind of surveying technique that a surveyor would use to lay out a plot of land from two different observing positions to a far-off object. Nobody had observed it with the accuracy that Halley wanted when he returned back to Europe. But this idea of measuring the distance of Mercury became important to him, because he realized too that according to Kepler's laws, if you could measure the distance accurately of any known planet, you could use it to calculate the distance of the Sun as a proportion, and hence calculate to a new level of accuracy the distance between the Earth and the Sun by these two incremental observations added together, the Mercury distance and the Sun distance added to it. Why did you want to know exactly the distance of the Sun? Because at this time, Robert Hooke, Halley, Christopher Wren, and eventually, of course, Sir Isaac Newton, are putting together those pieces of what would become in 1687 a universal theory of gravitation. Gravitation was concerned with distances and proportions, and worked on the assumption that if you could measure one proportion accurately, you could use it to extract the others. Therefore, measure accurately the distance of the Sun, and you can slot in the distances of everything else in the solar system, using what were seen to be eternal laws of proportion. This is why, therefore, there is such an enormous wish to know the distance of the Sun accurately. What Halley does there, he says, yes, Venus transits are much, much better than Mercury ones. Mercury transits are so fast, you flick and you lose them. Venus is bigger, slower moving, easier to observe, but unfortunately, not a soul on the face of the Earth at the moment in 1680 will live to see one. After all, 80 years into the future. And this says something about Halley's sense of his duty to the future. Over the course of the next 20-odd years, to 1715, he publishes a series of major papers in the Philosophical Transactions of the Royal Society, the most preeminent scientific journal in Europe, still is. And in that journal, he refines a set of figures for the 1761 transit of Mercury. They're written in Latin. The intention is they are able to be read by any of what we call the cognoscenti, the scientific connoisseurs of Europe, even if they didn't read English. After all, every educated man in those days read Latin. So therefore you write your big stuff in Latin, because that will get it read all over Europe. He knows, though, he will never live to see the transit he has publicized. In fact, though, he doesn't miss it by that much. He misses it by 19 years, because Halley is 86 years old when he dies. And he dies still in office as Astronomer Royal, as he later becomes. And I might just say in passing that his death was probably one of the most felicitous in the history of science. Halley was very fond of sherry, and he also liked tobacco. And Richard Mead, his doctor, had effectively said, try basically to cut back on what you like to tipple most of all. And when he was 86, his son-in-law was visiting him, and he sneaked a large bumper of sherry. Not a glass, we're talking sort of small jam jar size, full. That's how they drank it in those days. And it was said he downed it, sat in his chair, and breathed his last, which is not a bad way to go. There's no doubt. And of course, Edmund Halley, that's why I think Halley has such a charmed life. But the key thing he's done about Venus, he has made sure in the international language of Latin that everybody knows what's going to happen in June 1761. And time goes by. And then a Frenchman by the name of Delisle, working in Paris, by the 1740s and 50s, he starts nudging the French learned establishment about what's going to happen in a few years' time. His nudging also catches on in England and in Italy and in Holland. Leiden, of course, was one of the great universities of Europe by this time. And there is a gradually held opinion that as many astronomers from as many countries should observe the 1761 transit of Venus from as many far-flung corners on the Earth's surface as possible. And hence the French and the English governments, or more correctly, the Royal Society of London and the French Academy of Sciences, start to prepare long-distance observations. Siberia, India, the Cape, long way away. The intention being, therefore, if you have, let's say, 50 or 60 astronomers in various parts of Europe observing it from, let's say, Madrid to Sicily to Edinburgh, that kind of thing, then lots of others right in far-flung places around the Earth, then you'll have this great web of triangles from which you can then measure accurately the distance of Venus. Telescopes had also got vastly better by 1761, so the chance of a good observation was much, much better. There was only one problem about 1761. England and France were in the thick of an extremely bloody war. Now, you may wonder, would this have completely ruined it? Well, no. Wars were different in the 18th century to what they later became. We tend to feel, probably from 20th and post-20th century experience, that wars are fought ideologically. They are fought because one group of people utterly hates, detests, and abominates another group of people, or wants to wipe them out, whatever. This is not how you fought in the 18th century. Whether you were a Frenchman, or an Englishman, or a German, or a Dutchman, or whatever, you all effectively belonged to a group that had a lot in common. A classical education, a love of music, a love of natural philosophy, the Christian religion. You would have had a lot more in common with a Frenchman, with a German, than, let's say, a person would have today with, let's say, an Iranian, or the way in which wars are fought today. The cleavage planes were very, very different. So therefore, why did these people fight each other so much? Basically, it was sort of scrapping in the playground wars in the 18th century. I want that valley in Germany, you keep out of that valley in Germany, or else I'll bring my army to keep you out of it. Or, I want your daughter to be married to the king of my country, she's ugly, he won't marry her, I want compensation, scrap, 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 that kind of thing. That's what 18th century wars were for. They weren't fought about big ideological differences. Now, they weren't wars to annihilation. Like we think that wars often are. You would have had these men who would, on the battlefield, would have fought absolutely like tigers and with immense courage to each other. When they weren't actually fighting, they would play cards, they would drink sherry, they would maybe duel, but yes, they'd get on because they belonged to that class called gentlemen across Europe. And whether you were a Frenchman or a colonial American or so, if you're in that group, it didn't really matter. Now, this therefore tended to mean that even at the height of a series of wars like the 7 Years' War, you could have both countries willing to honor each other's groups of scientists. And this meant, therefore, that both the Royal Society and the French Academy of Sciences actually swapped over what they called passports to each other. So that if a ship was going to somewhere and it was stopped by another vessel of the enemy side, you could show this piece of paper and say, all right, on your way, yes, you're scientists, you're not fighters, yes, yes. That's the theory. The thing is, captains of warships are fighting men. And they might be carrying a group of scientists to some far-flung corner in the end of the earth, but nonetheless, if they see the enemy flag, they'll go for it. And frankly, pieces of paper become irrelevant. And this is what actually happens. 1761 produces a saga of men whose expeditions go spectacularly wrong because of war. First of all, let's start off with Charles Mason and Jeremiah Dixon, the men who would later become immortalized as the surveyors of the Mason-Dixon line in North America. They were commissioned by the Royal Society at a very hefty fee of 200 guineas each to go to India to observe the transit of Venus. Now that, of course, was a long haul, about a 10-month voyage, and you had to start it at a particular time because you had to get it where you got what they call the Indian winds. By the time you'd got to the Cape of Good Hope, if you'd missed the winds, the monsoons that would blow you up to India, well, you had to wait for another several months. They were to go on a warship, a frigate, HMS Seahorse, and they sailed from Plymouth. So they were therefore sailing as two private civilian scientists on one of the King's men of war. 4 days out of Plymouth, they meet a French frigate out of Brest. All the beseechings of Mason and Dixon to the captain of Seahorse are water off a duck's back. Frenchman, bang, get him. Even when flags are run up to inform the French ship that there are English scientists on board on an expedition approved of by the French Academy of Scientists, irrelevant. A ding-dong battle takes place, a sort of hornblower sea fight. Mason and Dixon, terrified out of their utter wits, are down in the bilges to get as far away from the flying shot as possible. Seahorse loses 11 men dead and 30-odd wounded. She creeps back into Plymouth, battered. Neither she nor the French vessel had won. The French ship was put back into Brest, equally battered, as a draw. Mason and Dixon swear they will never, ever, ever go near a ship for the rest of their lives. The Royal Society threatens legal proceedings. They drag things on a bit, and then they say quite correctly, but yes, it's delays, we've missed the winds. We won't get now to India. Right, you may not get to India, but you're going to South Africa. They then get put into a ship. Obviously, of course, they would have had consent. Then also, French expeditions, how do they fare? Well, you have a number of spectacularly unsuccessful, by that I mean by the sheer fortunes of war, French attempts. Alexander Guy Pingret, who was a French aristocratic scientist, is to go to an island called the Ile-de-France, which would be one of the islands in the Mauritian chain, to observe it bang in the Indian Ocean. He gets there, fortunately, on a French man of war, observes it, and gets his transit results, but shortly afterwards, an English frigate turns up, commanded by one Captain Robert Fletcher. Pingret, with of course the gentlemanly diplomacy of the day, shows him his English charter, stamped by the Royal Society. Effectively is told, whose leg are you pulling here? And he basically has some of his equipment pinched, his stuff broken, but nonetheless he gets back to France with his results. But then you get other problems. For instance, you have the situation of Chape de Haute-Rocher, who is sent by the French government, not on a sea voyage, but a colossal land expedition to observe the transit of Venus from Tobolsk, right up on the edges of Siberian Russia, well to the northeast of Moscow. You've got to get there not merely for June 6th, you want to get there by mid-April, because the observation procedures of the day required you not only to take a telescope, but also an accurate pendulum clock, specially packed in a case, a quadrant, various instruments for measuring your position. You were supposed to get to wherever you were going to at least 6 weeks before the transit was due to take place. Set your clock up, set it on the sun, time the exact daily equation of time, as it was called. Then you could use this for fixing exactly where you were on the Earth's surface to within, hopefully, a quarter of a mile, vis-a-vis Paris or Greenwich or somewhere like that. So you had to be there well in advance. How did you get to Tobolsk for mid-April? You traveled through the Siberian winter. It was as simple as that. How do you start your journey? Well, poor old Chape de Haute-Rocher can't even just go the normal way. You can't go via Berlin and so on, because, of course, the Rhine is a theatre of war. The English are backing the German princes against the French. And so, therefore, you will be in the thick of military engagement if you try to go straight to the east. He therefore has to have this extraordinary detour around southern Europe. He actually crosses Siberia in the depths of winter on sleds. And he leaves in the narrative he subsequently published how he woke up in the middle of the night in one of their campsites and found that none of their Russian guards were with them, or teamsters or anything were with them. There was him and a couple of Frenchmen. They then loaded up a pair of pistols, and he mentioned they could hear wolves howling in the darkness. Moreover, the only illumination, he says, was starlight reflected from the snow. So it's pretty dark. And they found with a lantern footsteps in the snow. They traced the footsteps to a local village where a local feast is being held, where their guides have slunk off to the feast in the middle of the night. They bring them back at gunpoint. All of this delays the expedition. And one of the great problems which they face going to Tobolsk is that Tobolsk is on the opposite side, on the eastern side of the Tobol River. The Tobol River was 1.5 miles wide and a solid ice sheet. They approach it just as the spring thaw is setting in. They were told that the ice was breaking. And what Chapter Autorocher and his companions do, they get their sleds and their equipment and everything. They don't say whether they leave their Russian guides behind. They whip up the horses and literally fly across the ice. He mentioned that they could hear the ice sheet cracking under their sleds. But they get to Tobolsk. And he records the day after, the ice broke and the river became liquid. You may say, why didn't he wait another day? That would have been useless. Wait another day, the ice would have been there for another month. So simply it would have been impassable in a boat for another month. This mad rush in a sled upon the ice. But then there is perhaps one of the most unfortunate figures and returns to in the history of science with good observations. Jean-Baptiste Hyacinthe Legentil, and he has several other names as well. He is sent out at first to Pondicherry in India to observe the transit for the French government or for the French Academy at Pondicherry. Now, let's have a little bit remembering here what history is taking place. The 7 Years' War is that period which effectively creates the groundwork of the British Empire. It gives us Canada, it gives us India. And in consequence, therefore, India, at the beginning of this cycle of wars, is not entirely controlled by Britain. Parts of it are still controlled by France. Pondicherry, as far as anybody back in Paris knew in 1759, was still French. But that was a long, long journey away. When Legentil gets there, he finds from ships off the coast that it's fallen to the British. Now you may say, no problem there, he's got his letter of marque, he's a scientist, sail in, show his certificates, yes, he can observe gentleman to gentleman. But no French captain is going to sail his ship into an enemy port and have it taken off him, his career destroyed, cashiered, all the rest of it. He puts back to sea. And on the day of the transit, we're told it was a brilliant, clear day. They knew exactly what was happening on the sun's disk, and they were forced to observe it from the quarterdeck of a pitching French man of war, where, of course, they just could not get anything stable at all. Legentil has a bright idea. I'm not going home. I'm going to stay in the region of India, in the Indian subcontinent and the Indian Ocean, and wait for the 1769 transit, and spend my intervening years studying the language, the culture, the geology, the botany, the ethnology. These men were not just astronomers, they are utterly wide-embracing philosophers, to observe all of these things. And that's what he decides to do. But there's one problem shared by every observer of that transit, which they hadn't expected before. And this is a thing which they called euphemistically the black drop. Now, the black drop goes back to the fact that, as Horrocks realized, Venus has an atmosphere. They expected to see Venus just beautifully and blackly moving, a sharp, hard disk moving onto the sun. But that didn't happen. When Venus touched the solar edge, Venus became a blob. And as she moved into the sun, a long black filament, the black drop, came about. And the great problem with this was, you couldn't be exactly sure when the edge of Venus had touched the edge of the sun. This meant that all the results collated when they got back to Europe had an error discrepancy bigger than anybody had expected. And this did not give the decisive solar distance. But everybody was saying, 8 years' time, we'll have another go. By 1768, when they're planning the 1769 expedition, Europe is at peace. Not only, of course, do you have the French and the English cooperating overtly, happy diplomatic relations, no problem there. And so it seems that these expeditions will be better. There are more of them. For the first time, for instance, a thing occurs which I think is a record as far as American history is concerned. John Winthrop, professor of astronomy at Harvard, takes a group of astronomers up Baffin's Bay, get well up to the northern Canadian latitudes, hopefully, to observe the transit from there. I think this was probably about the very first time you had an American scientific expedition being sent outside what was then, of course, the American colonies. And some of the old names reappear. 1769, the French send Chapman de Haute-Rocher now to California. He's to observe right the far distance round in California. And he has good results. But how do you get to California in 1768? You don't cross the American continent. You take a ship right through the Caribbean, you cross the Darien Peninsula on mule, and then take a Spanish ship up the coast to what was still then called Spanish California. But they observed good observations and got good results. On the way back, though, the entire expedition was blighted with yellow fever. Only one man survived, the French engineering officer who'd gone as what you might call the technical fixer of the expedition. Chapman de Haute-Rocher dies in the Americas. And one single man gets back problems going around. You have people going again into the Russias. You have an Austrian Jesuit with a wonderful name, Maximilian Hell. And Maximilian Hell is sent right up to the most extreme northwestern point of Europe, the River Vardar, right up the Gulf of Bothnia in Lapland, about as far up Europe as you could go. He is to observe it there. Also, too, none of these people are just going observing a transit. They're looking at everything else around them. And in fact, Maximilian Hell writes one of the first treatises on Lapland. Its geography, its location, its climate, how the Laplanders depended on certain types of animals to give them sustenance throughout the year. All of these kind of things. So they're great encyclopedic expeditions. And then you have Captain James Cook. The Royal Society decide by 1769 they want an Antipodean expedition. They want one, as it were, like a needle stuck right through the earth. And if all of these observations are going on in Europe, you want somewhere right through the earth at the far end of Europe. The recently discovered islands of Otaheite were considered a good place to go. Otaheite had been discovered by an English captain crossing the Pacific a few years before. They were not only bang in the right place physically on the Earth's surface, they were also seen as paradise islands, a benign climate, spectacular landscape, abundant food supplies, animals to eat and so on, and very, very importantly, friendly, easy to get on with native population. The problem was, how would you get back to Otaheite? It had been originally discovered by utter chance. Now, yes, you knew where they were, in the same way that you know where, let's say, in European terms, you know where Bournemouth is in relationship to the whole of Europe. I mean, it's somewhere in a big mass. But you imagine, you know, somebody comes in from the sea and they're trying to find Bournemouth and not quite sure whether it's in Lapland or whether it's in Italy or it's just somewhere in a big... That is the Otaheite problem. They knew it was in a big chunk of the Pacific, small on the Earth's surface, but very, very hard to find in detail. At that time, there was no reliable captain who could find that position. And I may, of course, mention that the word Otaheite comes to be, as it were, anglicized or Europeanized to Tahiti. Captain, or as he was then, Lieutenant James Cook, was chosen by the Admiralty to take that expedition. Why he was chosen? He was known to be the best surveyor and the best navigator in the Royal Navy. He was a master astronomer who had mastered the recently developed techniques of finding your longitude by lunars from the moon's position, which required not only a very, very high degree of astronomical knowledge to do it, but a very, very high level of mathematical competence as well. Most naval captains and naval officers in those days weren't, generally speaking, big on navigation. They were big on fighting. That's what they were there for. And most of the wars of that period were in what you might call the enemy in easy-to-find places, such as off Jamaica, or off southern Spain, or off Sicily. In other words, well-run sea routes. Captains and sailing masters in the Navy could find that, yes. But find a little group of islands in the middle of the Pacific, that was a totally different technical exercise. That needed real astronomy and real mathematics. And that's why Cook was chosen to take the expedition. He was commissioned into a ship of his own choice, and this became HMS Endeavour. He chose Endeavour because Endeavour was a converted, quite new Newcastle collier ship, or Whitby collier. The colliers were wooden vessels capable of taking an immense battering in the storms of the North Sea, very, very high internal volume because, of course, they were taking coal, and immensely seaworthy. Also, they had an enormous advantage, better than any of the normal ships in the Royal Navy. They were very low draft in relationship to internal volume. Cook knew, although he'd never been there, Cook knew from report that the biggest single hazard in the Pacific was coral reefs. And this meant that the slightest draft your vessel had, the less chance you had of hitting them. And this is a model of HMS Endeavour. This is in the National Maritime Museum. It's an authentic model to show you what Cook's ship was like that took the expeditions around to Tahiti. Cook sailed out, and with him on board the vessel was the Royal Society's official astronomer, Charles Green. And then there was another entourage, because, quite frankly, Endeavour must have been an extraordinary floating expedition when she went down the English Channel towards the autumn of 1768. The principal figure was, of course, Sir Joseph about 10 months, a Lincolnshire baronet, naturalist and future president of the Royal Society, who'd become a great chum of Cook's and would remain so. And he took with him a number of friends. The Swedish doctor, botanist, Daniel Solander. The official artist of the expedition, Sidney Parkinson. Plus his pet greyhounds. Greyhounds on a 120-foot boat. Goats to make sure that you had fresh milk for your coffee. And various other little luxuries. This was the expedition that sailed out. He hit Tahiti bang on the nail. The success of the observation was utterly unqualified. Cook saw everything they intended to see, and of course saw it right the way around the Earth at a different time and in a different position to what it would have been seen by any European. But then when he sails away from Tahiti, he has his so-called secret orders. And these secret orders are not to come straight home. They are to cross the equator, sail 40 degrees south of the equator, and then turn right, effectively. So straight down the equator, then turn west, and then circumnavigate the Earth at the 40th parallel. See what you find. He found what the geographers were calling euphemistically beforehand, terra incognita australis, the great unknown southern land. It comes to be known, of course, as Australia. And why, of course, Botany Bay comes to be called Botany Bay is because Joseph Banks, the great, great field botanist of the age, finds more species of flowers in a few acres of grass that were totally unknown in Europe. And he said because of the exotic nature of the fauna, He called it Botany Bay, of course, later to become notorious as a penal colony. And then the expedition returns to England, and Cook, of course, is fated. But we must now go back to Le Gentil, who'd stayed right the way through in this entire period to observe the transit of Venus. He goes back to Pondicherry for 1769. It's in British hands now, but that doesn't matter. The governor of Pondicherry is Mr. Robert Law, and when the French savant appears, he is given the warmest welcome. He is put up in the governor's mansion. The governor, of course, Law himself, is a man of culture, and he says, observe the transit of Venus, I'd love to observe it with you. And he has an observatory built on the old fortifications of the town. He even obtains for him something not available in 1761, a new Dolland achromatic refracting telescope to observe the transit with. Both men, for 1769, plan on observing together, the governor and the Frenchman. We're told that the day dawned brilliantly and clearly. The sun rose, and at about the time of the transit to begin, a single thin wisp of cloud moved across the sun. By the time the cloud moved, the transit had started. He saw the transit, yes, but he didn't see the crucial beginning, which would of course have been crucial for calculation. After this, Le Gentil is not in a terrible hurry to get back home to France. And by the time he gets back to France, he hasn't been in touch for a few years. And by this time, he's finding that his relatives are now haggling about the prosperity of his estates. And they're being confiscated. And he has to go to law as an attempt to restore his own estates. And after this massive mess of litigation, the French Revolution eventually breaks out, and he is forced to flee to England, where he dies in, I think it's 1808, in relative poverty. I think the story of Le Gentil is probably one of the most tragic in the history of astronomy. But what this transit had done, the 1769, was they were now waiting for the black drop, and they were able to take compensatory measures. And the figures for the distance of the sun from the 1769 transit were within literally a tenth of an arc second of a decimal place to the figures we use today. In other words, they gave you the solar distance at about 94 million miles. Astonishingly good. Now, this gives you some sense of the technical development of astronomy by that time. There were, of course, two other transits, 1874 and 1882. But they really are fairly easy to tell. You see, you didn't need much in the way of expeditions by that date. By the 1870s and 80s, steamships crossed the world. Australia, all of these countries, America, were actually populated. There were transcontinental railways across Siberia, across America, and even a telegraph line across Australia. Telegraphy made it possible to have your results back in Paris or in New York or wherever within hours of the transit. In 1872, for instance, the first Australian wire had been laid. We were in constant telegraphic contact with Australia by that date. Even countries too, which had actually then become part of a British presence, or other cultures too which had warmly and rapidly embraced European science, particularly Japan. And Japan, of course, had rapidly developed Western science, Western medicine, and there were several observatories in Japan that observed the transit in 1874 and 1882. Not as expeditions, but being done by indigenous Japanese scientists. And so you have, by that time, literally global cover of the transit. You only have a few distant expeditions. The British, for instance, sent a famous expedition to Hawaii. Of course, obviously, by that time, westernized, colonized islands for good or for ill. Yes, to the devastating effect of the native population, one can't deny. But yes, there have been made crucial observations there. Only one that I'm aware of was sent to an utterly desolate place in 1874. An English ship was sent to Kerloigan's Island, and I think that you will need to look fairly closely on an atlas to find Kerloigan's Island. It's more or less between Northern Australia and South Africa, deep down, approaching the Antarctic. It really is a hellhole. Freezing, cold, wet. Its sole occupants, penguins and birds. But it was used as a maximum southerly location, and it got good results. Now, on the 8th of June this year, hopefully you'll see the transit. If you're going to observe it in, let's say, Bournemouth or some part of England or some part of Europe, fine. But if you choose, let's say, to combine it with a holiday to Australia or, let's say, America, California, or even for that matter, Siberia, just imagine the enormous problems, the courage, the determination, and the sheer ingenuity that was necessary to observe those 18th century transits, because they were quite apart from their scientific content. They were utterly monumental sagas of primary exploration in their own right. Thank you.